Hey everybody, today we are going to talk about valence electrons, the octet rule, Lewis dot diagrams, kind of giving you an overview of what's going on with bonding. Okay, so this is the first item, the first podcast in bonding. Right. So far all we've studied are atoms, and atoms are very limiting because we've only got 92 of them on the periodic table, so that's all that exists. In fact, because if you look after 92, all of these masses are all one isotope, and that's because they've been made in a lab. They do not exist in nature. In fact, that's also true for technetium, which is over here, number 43. Technetium also has only been produced in a lab, so it doesn't exist in nature. So we only have 91 types of atoms to play with in the world. So isn't that limiting? Well, not really, because we can put them together. So we can put H2O or CO2 or sugar. Wouldn't the world be boring without sugar? Okay? So anyway, what we're looking at now is how we put things together. So we have three types of bonds, and ionic bonds are the strongest ones. Everything that's ionic in nature is all a solid, and an example would be salt is an example of ionic bond. And then we have metallic bonds. Metallic bonds are things like between two metals, or in fact it can be within a single metal, like this is aluminum foil. And then down here we have covalent bonds, something like water. Right? And covalent bonds, everything that's ionic is a solid at room temperature. Metallic, almost all are solids at room temperature. There are very few, like mercury, for example, which is a liquid at room temperature. And then we have covalent bonds. An example of that is something like water. All right, please pause the video and write these down. This is important stuff. All right, valence electrons are the electrons in the highest occupied energy levels, and what we have to focus on here is highest energy level. That's important. Okay, and we're going to talk about how we know that. Okay, valence electrons are usually the only electrons used in chemical bonds. Now, I say usually because there are some elements that do some funky things, but we're not going to worry about those right now. Okay. Let's say that we're in a classroom and we have something in the middle of our classroom that's very, very important. So we surround it with a bunch of people. In fact, we surround it with layers of people or shells of people. And then over in another class, like let's say Mrs. Can's class, we have another something important that's surrounded by another bunch of people. All right. Now, if these two bunches of people run into each other, who's going to be impacted? Well, of course, it's the people on the outside. It's the people here. Okay. And it's the people on the inside aren't going to be affected. It's going to be the people on the outside who take the brunt of the punishment for banging into each other. Well, that's the way electrons work too. We only care about the electrons in the outermost shell because all of the ones that are on the inner shells, they're all protected by the ones that are on the outer shells. So we care about the outer shells, so that's what we're going to focus on. When we look down our groups, remember if we look down a group, we have similar chemical properties. So, for example, if we look down the furthest group on the right, which is the noble gases, they're all gases. Right? So they all have similar chemical properties. They're all gases. They don't go, well, that's physical property. They don't all, none of them react. That's chemical property. Looking at the first column, which are the alkali metals, and you should have watched a video on both the noble gases and the alkali metals in a previous unit. You should have noticed that their chemical properties were all the same. They all reacted with water. They all got more and more violent in their reactions with water, but they all reacted with water. So how in the world do we determine what the valence electrons are? Because those are the ones that are involved in those reactions. Well, let's look at some abbreviated electron configurations. So as a review, pause the video and see if you can come up with the abbreviated electron configurations for these things right here. All right. For fluorine, it is helium followed by 2s2 and 2p5. For chlorine, it's neon followed by 3s2 and 3p5. For bromine, it's argon followed by 4s2. Now, you have to be careful here because we have a 3d10 thrown in the middle, but 4p5. And the same for goes for iodine. After argon, it's krypton. And that's 5s2. Again, be careful because we have 4d10 thrown in here. And then we have 5p5. And you notice that all of these end in s2 and p5. Right, now here at our second energy level, we have 2 electrons at the 2s level and 5 electrons at the 2p level. If we add those together, we have 7 electrons. Now, if we also look here, we notice that we also have 7 electrons at our 3rd energy level, which is our highest level. Now look at bromine. You have to be careful here. We only look at the 4th energy level because it's highest. We can kind of ignore these guys in the middle because they're at the 3rd energy level. So we still have, at our topmost energy level, we still have 7 electrons. And the same goes for iodine. So you'll notice all of these, which are in the same group, the same column, the same family, all called the halogens, they all have 7 electrons in their outermost shell. That's why they all react the same way. So is there an easy way to tell how many valence electrons they are? Well, here's what I would like you to do. I would like you to pause the video, find a periodic table, and I'd like you to fold it right there along that line. Okay, I have done that with one of my periodic tables. I've taken a periodic table and I've folded it right here along that line. Now what I would like you to do is take that line and fold it, and fold the entire periodic table and take it over until it hits here. Right? So what happens when you do that is you fold it and you make it come in like this. And when you're done, you should have a periodic table where you're only showing the main block elements. The S block elements over on the left-hand side and the P block elements over on the right-hand side. Now, if you remember how these columns are labeled, they're labeled 1A, 2A through 8A, 1A all the way up through 8A, if we use that convention, as opposed to 1 to 18. And those are also happens to be the number of valence electrons that are in each column of the periodic table. So if you pause the video, please, and write down 1 through 8 as your valence electrons. Now notice we did ignore the D block and the F block, and that's okay, because we've already shown how those are all at a lower energy level than the electrons that are in the main blocks. So we essentially don't have to worry about the D and the F blocks. We can focus purely on the main blocks for right now. All right, so we have something called an octet rule. And again, pause the video, write this down. Atoms tend to gain, lose, or share electrons in order to obtain the electron configuration of a noble gas. So if we look at the electron configuration of a noble gas, let's say neon, that electron configuration is helium, followed by 2s2 and 2p6. Now, this is the electron configuration of a noble gas. If you remember, when we looked at our last set of podcasts, we talked about how all of your orbitals, when you hit here, are full. Your 2s orbital is full and your 2p orbitals are full. Right, well, if we look at fluorine, fluorine is almost full. Fluorine has 1 less electron than neon, so it ends in 2p5, so we're 1 electron short of being a noble gas. So what our octet rule tells us is that atoms tend to gain or lose or share electrons in order to obtain the electron configuration of a noble gas. Well, to get from, this is a total of 9 electrons, to get to a total of 10 electrons, all we have to do is add 1. So if I change that to a 6, I've added 1. But if I add an electron, what did I do to the charge of my fluorine? Sure, I made it negative because I added an extra electron. So this fluorine ion now, it's an ion, it's no longer an atom, has a charge of -1, and it has 1 extra electron. Well, how about sodium? Sodium, I'm going to write it this way, even though it's not correct. Just bear with me. All right. Well, let's write it the other way. It's neon plus it is 3s1. Well, gosh, if I lose this 1 electron, I have 11 electrons. If I lose that 1 electron, I'm going to have 10 electrons. I'm going to have the electron configuration for neon. Oh, how cool. But what happens if I lose an electron? Well, if I lose an electron, sodium is going to become positively charged because I have 11 protons and only 10 electrons. So atoms tend to gain or lose these electrons, and as a result, they become ions. So what is actually going on here? We need to make one point, and we'll hit this again in a later podcast, but I want to hit it now too, just so that you can remember it. If we have an ionic bond, we're gaining or losing electrons. If we have a metallic bond, or if we have a covalent bond, we are going to be sharing electrons. Okay, so why don't noble gases react? Well, we talked about the fact that they end in P6. And when they end in P6, when they're going to have S2, remember, and then they have P6, they have a total of 8 electrons in their outermost shell. And as a result, they're not going to react because all of their orbitals are full. Have to remember that. All right. And Gilbert Lewis noticed that back in the early 1900s, and he asked that question. He said, why don't noble gases react? Well, he came up with something to represent with X's and O's, typically dots. They represent valence electrons. And he said, the octet ones, the ones that are at the end, the noble gases, they're the ones that are most stable. So he said, let's go and model something with dots for electron configurations. Now remember, we looked at, as we worked our way across the periodic table, we said we started with column 1 and we went to column 8 at our noble gases. And those are how many valence electrons we have. So if we look at lithium, lithium's in column 1, which means it has 1 valence electron. So I draw 1 dot next to it. Now, I could draw the dot on the left or above or below. It really doesn't matter. Beryllium is in group 2, so it's going to have 2 dots. Right? Now, again, those dots could be on either side. They could be top, bottom. I do not tend to draw them together. I tend to draw them separately. So there would be boron with 3 and carbon with 4 because boron is in group 3 and carbon is in group 4. Well, how about nitrogen? Nitrogen's in group 5. Well, nitrogen, I'll put 1 dot on each side. And then I'll put 1 pair. There are my 5 electrons, and I put 2 together. Right? In an oxygen, I would do the same thing. I would do 1, 2, 3, 4, and I would do 5, and I would do 6. Does it matter where the double ones go? No, it doesn't. Top, bottom, left, right, doesn't make any difference. Right? Fluorine has 7 because it's in group 7A, and neon is the last one, and you'll notice that it has pairs of electrons all the way around it. It has 8 electrons, and neon is the most stable. So fluorine could gain 1 to go right there, and lithium could lose 1, and then it wouldn't have any in its outermost shell. Well, then it would go down to its next level. All right, see if you can do the electron configuration for magnesium and then the Lewis dot diagram. Pause the video, see if you can do that. All right, magnesium is, well, if I draw the abbreviated electron configuration for magnesium, it's neon, and then it is 3s2. So all I have to do is draw those electrons at the outermost energy level. So I've got magnesium, and I'm going to put 2 electrons up there. And that's it. All right, so you try a few. Again, pause the video, see if you can do these, and then I'll come back and do them for you. All right, phosphorus is in group 5, so it has to have 5 electrons around it. Calcium is in group 2. Krypton is a noble gas, so it is in group 8A or 8, and it is going to have 8 electrons. Aluminum is in group 3A or 3, so it has 3 electrons. Rubidium is in group 1, so it only has 1. And silicon is directly under carbon, so it has 4. Okay, folks, there are 3 types of bonds you need to know about: ionic, covalent, and metallic. We're going to talk about those in detail in the next few podcasts. You need to know the octet rule. Atoms tend to gain, lose, or share electrons in order to obtain the electron configuration of a noble gas. We'll talk about that a lot in the next couple of podcasts. And you also need to be able to do Lewis dot diagrams for atoms because we're going to be building on that and using them to build molecules in the future. All right? Thanks a lot. See you in class. If you have questions, let me know. Have a good one. Bye-bye.